Hello.
Hello.
So I hope I'm audible. Let's start today's lecture. So we'll wait for 2 more minutes and then we'll start. Okay, so we'll start now. I'll just confirm that I am audible. Just 1 minute. Yes. All right. So I hope I'm audible. So I'm Shubham Keshri, and I'm a PhD scholar at Department of Management Sciences, IIT Kanpur. I am one of the TA for this course, Strategy and Introduction to Game Theory. So this is an 8-week lecture course by NPTEL team. And some ground rules. So how this discussion session will move forward is that we will solve problems, and in case you have questions, you can just unmute yourself and then ask questions. And you will not have an option to chat or text, send a message. So please unmute yourself and speak. Otherwise, we'll not be able to communicate. Okay. So this is the problem. In last class, we were discussing this problem, and we had a question. So first, let me read this question. This talks about consumers have a preference in a uniform distribution between 0 and 1, and at along one point in a straight line. So in last week's lecture, we had this problem, and this problem had actually asked about, can we say that the Nash equilibrium at each firm when it is located at 0.5 or not? So this was the question, and we had actually 4 firms over here. And in last class, I had asked an additional question. The question was, what is the Nash equilibrium of this game? All right. So what this problem is, we have an interval 0, 1, and in that interval, there are 4 firms, and each consumers will purchase only 1 unit of good from the firm, all right, which is closest to him. If more than 1 firm are located at equal distance, the consumer will buy with equal probability from each firm. For example, if one firm is at 0 and other 3 are at 1, 0.5% of the market will be taken over by firm, the firm which is at 0, and the rest, which is 0.5 by 3, will be divided between the 3 firms which are at 0.1. Okay. So what will be the Nash equilibrium of this game? You see, we have 4 firms, and those firms will go to those points in which they get equal number of customers or equal consumers. So if you divide 0 and 1 in this interval, if you divide this interval into 4 parts, it will come out to be 0.25. So each firm, when each firm has a market share of 0.25 or 25%, then there will not be any incentive for any firm to deviate. All right. So we'll have to divide this interval 0, 1 such that each firm gets 0.5. Now you see, if you mark this, if you divide this section in 4 parts, 0.5, 0.25, 0.5, 0.75, and 0.1, you see these 4 regions are equally divided. And if each of the firms are situated at the midpoint of these locations, these are the firm's locations, then each firm will have a market share of 25%. So this will be the answer. So this is so this is 0.125 and so on. Okay? So this will be 0.375 and so on. So I couldn't complete this in the last discussion class. So that is why I have taken this question over here. So again, those who have joined now, I'll let you know that you don't have an option to chat. So you can just unmute yourself and speak if you have doubt or any concern. All right. So shall we move forward?
Yes, sir.
Am I? Okay. Okay, so first what we'll do is, so in this week's lecture, we had a discussion on extensive form games. So this discussion hour is actually designed in such a way that we'll go from the basic ideas of extensive form game and then we'll move on to more involved questions. Right. So the first problem which we have over here is we have two players, player one and player two, and there is some game going on, extensive form game, sequential game, and you are asked to draw a game tree and then write down the strategies of the players. All right. So you have two players, player one and player two. Player one has two actions, A and B, and when player one has played the game, the next is player two will play. When player one has chosen A, then player two can choose X comma Y, and when player one has chosen B, player two can choose W comma Z. So this is a very simple question. You have to just draw the game tree. You can just unmute yourself and help me draw the game tree.
Two options, A and B.
Right. So you see, whenever you draw a game tree, so why this is called as a tree is because you see, this tree is a special case of a graph, and a graph in mathematics can be written as G, V comma A. So these things are not discussed in the lecture because it is not relevant, but for your information, I am telling you, whenever you write G, V comma A, it in mathematical terms, it means that this is a graph, definition of a graph, where V is the set of vertex or nodes and A, or you can write E also. So G, V comma E. This is also written. So E or A is the set of edges. All right. And a tree is a special case of a graph where all the nodes are connected and there are no cycles. So there are some properties for a graph to be known as tree. That is why this is known as a game tree. All right. And those properties which satisfies a tree will satisfy this game tree as well. Obviously, that is why we are calling it a tree. So this point which I am calling as 1, this is actually a node, and this node, at this node, player 1 is asked to play or supposed to play. That is why I'm writing 1 over here. And when I'm writing A and B, these edges, so these are edges between these two nodes, this node and this node. So in this edge, there is one strategy a player can play. It can either be A or B in this case. All right. So when player 1 has played A, what happens in these nodes, in these two nodes, when player 1 has either played A or B, player 2 is asked to play at this node. All right. And the the action sets are given. So at this node where player 1 has played A, player 2 can play two actions, which is X comma Y. And similarly at this node, the other node, player 2 can play W comma Z. All right. And over here, these are terminal nodes. These are leaf nodes or terminal nodes. All right. And the node at which the tree has started is known as the root node. And these are leaf nodes or terminal nodes. Why are we calling these nodes as decision nodes? This is because a player is allowed to play at these nodes, but these decision nodes are not actually a terminology taken from graph theory. These are given to just 1 minute. एक मिनट I'm sorry for the interruption. Okay, so what I was saying is, so this is the game tree, and this decision nodes, this terminology, decision nodes are not taken from the graph theory. All right, but these terminologies, which I have known, which I have labeled as root node and leaf node, these terminologies are actually taken from graph theory. And so now the next question is asked is, what are the strategy of player one and player two? Right, so you can just unmute yourself and speak. What are the strategies of player one?
Player 1 is A or B?
Player 1 can take any strategy from the set A or B. So this is a strategy set for player A. You can write it as S of A or any notations you are using. I am saying capital S of A denotes the strategy set of player 1, which has two strategies A and B. Similarly, player 2 can have multiple strategies. This set will be known as strategy set of player B. All right. Now you see, player 2 have multiple actions at different nodes. And if you have seen the lecture, then you will know how to identify the strategies of the player 2. So if you could unmute yourself and speak, or otherwise I'll help you define the strategies of player 2.
X, Y, W, Z.
So you're saying X, Y, W, Z. These are the strategies of player 2. Am I correct?
Yeah.
All right. So when you're saying the strategies set of player 2 is X, Y, Z, W, Z, this is not correct. Can anybody tell me why this is not correct?
So technically, all four are not available at the same time. X, Y is available at one time if
Right.
it is played A, or Y, W, Z. So it will be
Okay.
sets of.
So if you have, so whether have you seen the lecture, this week's lecture? There's no
Yeah.
issue. You can okay. So you see, when I say strategy and when I say action, in normal form game, both are same. But in an extensive form game, a strategy is different from action. All right. So when you say a strategy in an extensive form game, you have to define the uh, the steps which will be played in the game in any node. All right. So when you say the strategy of player 2, you have to specify. Suppose I am not going, I am asking someone as a proxy to go in the game, and I have to give what strategies I will play. So at each node, you have to specify what will be your strategy. So you see, when player 2, suppose I am saying play X when you are at this node and play W when you are at this node. So I should change the color. So what I'm saying is, suppose some person is going in place of me and I'm saying when you are at this node, play X, and when you are at this node, play W. All right. So this is what I am specifying to him. So you see, I have not specified 4 actions. I have only specified this combination X, W. So this is my strategy for this game. So if I ask someone to go on behalf of me, I would ask him to play XW. That is one strategy, and so on. So you can say either XW or XZ, YW or YZ. So these will be the strategies of player 2 and not XYWZ. Any confusion? You can unmute yourself and ask me. There's no issue in if you're not able to understand, we can just discuss this further. All right. So
Basically, you're saying that guy to whom I've instructed to go and play.
yes,
When I say XW, I'm telling him if it is the first term is for A and the second term is for B.
not A or
That is
B,
how.
A or these nodes, not A or B. A or B is, I know what your meaning is correct, but I'm correcting you on technicalities. So this node, when the game has come to this node, play X, and when the game has come to this node, play W. Or in the other hand, when player 1 plays A, then you play X. When player 1 plays B, then you play W. This is the complete strategy information. So this information you have to provide in order to play the game in all possible cases. So this is how a strategy is defined in an extensive form game. And this definition can be taken to normal form game as well. And in that case, strategy definition and action set definition or action definition merges and becomes same. And therefore, we are saying strategy and action in a normal form game are same thing, but not in an extensive form game.
So here, if this is a strategy, what will be the action?
So action is defined for a particular node. So when you are at this node, you can either take an action X or an action Y.
Achha. Okay.
So in sequential game or normal form game, both the players are playing simultaneously. There is no two different decision nodes where player 2 have to decide whether to give this action or that action. Over here, there are multiple nodes at which player 2 is making decision. That's why you have this kind of strategy sets, strategies for player 2. Is this all right? Others? Any question? Because if this is not clear, whatever we are going to discuss next will be not clear. These are basics of what we are going to discuss next. All right, so I'm assuming that this is all right. So we have drawn the game tree and also written down the strategy set for player 1 and player 2. So this will help us in the next question. So the next question is, I have a normal form game. This is a normal form game. Can we represent this normal form game as a extensive form game given? So I have not written the complete question. The question is given player 1, or you can, this is not required. Just the question is, can you represent this game as extensive form game? All right. So can we do that? So you see, you can define nodes and you can say, suppose player 1 has two actions. Not suppose, obviously player 1 has two actions, heads and tails. All right. Now player 2, and this is a sequential game, not sequential game, this is a simultaneous game. So player 2 is not the second player to play. So this is how we represent a normal form game in a sequential game. We draw a dotted line between these two nodes and we say that player 2 is not sure whether he is at this node or at this node. So both these nodes are indistinguishable for player 2. And at this node, the player can either play HT or, and this node as well, player 2. So this is for player 2. Player 2 can either play H or T. And player 2 cannot distinguish between these two nodes because this is a simultaneous game and player 2 doesn't know which node player node player 2 is in or what strategy player 1 has played. Therefore, this is the extensive form representation of this normal form game, and you have to write the payoffs as well. So when player 1 plays H and player 2 plays H, 1 comma minus 1 is the payoff. This is the payoff I have written. So when player 1 plays H and player 2 plays T, player 1 is playing H, player 2 is playing T. So the payoffs are minus 1 comma 1. When player 1, okay, I'm writing it in the opposite direction actually. So this is not correct. When player 1 is playing H and player 2 is playing H, it is 1 comma minus 1. When player 1 is playing H and player 2 is playing T, this is what it will come, minus 1 comma 1. When player 1 is playing T and player 2 is playing H, this will come minus 1 comma 1. And when player 1 is playing T and player 2 is playing T, this will come 1 comma minus 1. This is the complete representation of a normal form game as an extensive form game. Any questions?
So in this, if someone is asking what is the strategy of player 2, because it is dotted, you will not call it HH, you will just call it HT.
No, yes. Because this is dottage, this player 2 cannot distinguish between these two nodes, and therefore the strategies of the player 2 is only H and only T. So the set will be H comma T. All right.
Yeah, okay.
Do you have any doubt? All right, so I'm assuming there is no doubt. Sorry. So I'll just unmute you. If you have doubt, you can just, I'll just mute you. If you have doubt, you can unmute yourself. All right. Okay. So now I have a sequential game. So this is a extensive form game where player two, so I have not written player two, when player two is playing after player one has played. So this in this game, player one has already played and player two is taking decision after seeing what player one has done. So this is a different game than before. All right. And therefore we are not drawing the dotted line between the two nodes where player two is playing. Now the question is, can you write the normal form or draw the table for normal form game for this extensive form game or for this game represented in extensive form? So first tell me what are the players. Players are player 1 and player 2. Is this correct?
Yeah.
What are the strategies of player 1? Strategies of player 1 are H comma T. Is this all right? Strategies for player 2 are H H, H T. This is T. TH and TT. Is this all right? Now we can draw the game table easily. You see, we can just say player 1 and player 2. Player 1 has two strategies, H and T, and player 2 has HH, HT, TH, and TT. All right. So you can just write the utilities when player 1 is playing H, when player 1 is playing H, and player 2 is playing HH. So this is H and this is H. So this will be the utility. This is where the game will end. Therefore, 1 comma minus 1 will be the utility for this combination of strategies. Is this all right?
Yeah, understood.
All right. So in a similar way, we can fill up this table. So let me just fill up quickly. So player 1 is playing H and player 2 is playing HT. So when player 2 is playing HT, this will be the place where the game will come and we'll have 1 comma minus 1. Now when player 2 is playing TH, so he is playing T and then H, and player 1 is actually playing H, then this will be the utilities minus 1 comma 1, and this will also give minus 1 comma 1. All right. When player 1 is playing T, so player 1 is playing T, I'll change the color. Player 1 is playing T and player 2 is playing HH. So this will be the place where the game will come and you'll have the utility as minus 1 comma 1. Again, when player 2 is playing HT and player 1 is playing T, this will be the place where the game will come and it will be 1 comma minus 1. And this will again be minus 1 comma 1. You can just confirm and 1 comma minus 1. So this is the complete representation of this extensive form game in a normal form. So this is the normal form. And now you can easily determine the Nash equilibrium in this game. Is this all right? All right. So we'll just move.
Just
Yes.
can you just explain
Yes.
the second column?
Second column or second row?
No. I'll just tell you. When player 1 is playing H and
When player 1 is
2
playing H
and
and
player
player
2
2
is playing HT.
when player 2 is playing HT.
So
So when
this
player 1
one,
when player 1 is playing H, all right, and player 2 is playing H and T. So the game will end at this node, all right? The game will end at this node.
It's not at the T end.
Right, because player 1
that
is
guy is not
playing
playing T.
T.
Achha.
Just make sure is this okay, because we'll take this idea forward and then solve more complex problems.
Okay, so let me just check if player 1
Right.
is playing
So I'll
T
just, okay.
and this guy is playing H, so it will be kind of finished. Okay. Okay.
Alright.
Okay, yeah. Okay, understood.
Now, this idea is of subgame first. All right, so this is an extensive form game, and I have given here one game tree. Now the first question is, how many subgames of this you can find for this game? So if you have seen the lecture, you will know what a subgame is. And if you know what a subgame is, can you tell me how many subgames are there in this game?
So since there is a dotted line, there will be two subgames.
Which one are the subgames?
One is for player 2 because it's all connected, and one is the entire game.
This one and the other one is the
And the
entire
entire
game.
one. I
All
don't
right.
know if I'm
So
right.
if you, no problem. There's no issue in telling a wrong answer. Now you see, when you say, so I'll just mark this. This is one subgame and this is the other subgame. All right, I'm just marking it for reference. So when I'm saying one is a subgame, this is not correct. If you go to the definition of what a subgame is, in a subgame, you will have a single node at an information set. So if you have to see what an information set is. So at a node, player 2, for player 2, the nodes are, so I'll just label these nodes now. Suppose this node is 1, this is 2, this is 3, and this is 4. Now you see, for player 1, the information set will be only 1, because this is the point at which he's making decision, and there is only one point in that. Now for player 2, one information set will contain 3 nodes, 2, 3, 4. And when such things happen, then we cannot label this as a subgame. Therefore, 1 is not a subgame, only 2 is a subgame.
Okay.
All right, so we have this as 1. Now, the second question is, how many proper subgames are there in this game? So Aranganathan, if you have also a question, you can just unmute yourself and ask. All right. I just muted you because there was some noise. All right. So the next question is, how many proper subgames are there in this game? So what is a proper subgame? So a game, if its root node, or in simple terms, if the whole game can also be represented as a subgame, right? Over here, 2 is the whole game, and we are saying that it is a subgame because that is a subset of a set, can also be a subset of itself. Now, in sets, if you say proper sets, then you are saying that apart from itself, what are the other subsets it has? Proper subset. Apart from itself, what are the subsets it has? So in same sense, a proper subset is the subset or subgame in which it is not occupying the whole game. Therefore, 2 will not be a proper subgame. Is this correct? 2 is not a proper subgame. For a subgame to qualify as proper subgame, the whole game shouldn't be that subgame. Therefore, there is no subgame in this problem. Any doubt? We have only one subgame, that is the game itself, and that doesn't qualify to be proper subgame.
Okay.
You have doubt, you can just unmute yourself. So if there is no feedback, it's difficult for me to understand. All right. So there are no proper subgame in this game. Now the next question is, write down the strategies for player 1 and player 2. All right. I'll just erase these now. And the question is, write down the strategies for player 1 and player 2. So we have discussed these things. For player 1, you can just unmute yourself and tell me the strategy.
L, C, R.
L, C, and R. So there are three actions player one can have, and player one is making only decision at only one node. Therefore, the action becomes the strategy, and thus we have L, C, R as three strategies for player one. For player two, you see Y, N, Y, N, Y, N, but this is actually a simultaneous game where these three nodes are indistinguishable for player two, right? Therefore, player 2 will not be able to distinguish between these three nodes, and these actions yn will be same at all the nodes. Therefore, the strategies for player 2 will be y and n. That's it. Only two strategies. This is the strategy set for player 2. Is this correct?
Okay.
Now, the next question is find the subgame perfect Nash equilibrium for this game. So, do you know how to find a subgame perfect equilibrium or subgame perfect Nash equilibrium of a game?
So let it go from the bottom backward.
Right. So you can use backward induction. Now, backward induction has some limitations, because of which you will not be able to apply backward induction in this game. Can you identify what limitation of backward induction will make it difficult to solve this problem, or make it impossible to solve this problem using backward induction?
Well, you don't know which of those three nodes you are on.
Right. So you don't know what player. So player 2 doesn't know which node he is in. So you will not be able to apply backward induction. You see, at this node, player 1 is not sure whether player 2 is playing Y or N, right? So you see, I'll just help you. I'll just help you out. You see, at this node, player 2 can play either y comma n. You see, y is actually giving a higher utility. Therefore, at this node, player 2 will play y. In this node also, y is giving higher utility than n. Now, player 2 will play y, and over here also, player 2 will play y because it is giving higher utility. Therefore, in this game, y is a dominant strategy for player 2. Therefore, player 1 knows player 2 will play y. Suppose this utility for player 2 was not 0 and 2. Suppose this utility for player 2 was not 0 and 2. What will happen in that case? In that case, player 2 will play at this node y, but at this node, player 2 will play n. Is this correct? If this utility was 2. So
Yeah, but it doesn't know at which node he is.
Right. So you see, currently, so in this game, when I have changed the utility for player 2 at this node as 2, player 2 can play y or n anything. So player 1 doesn't know whether player 2 will play y or n. All right. So player 1 doesn't know whether player 2 will play y or n. Therefore, backward induction will not help him. All right. You will have to use some other ideas. We will discuss those ideas in this discussion session as well. And therefore player 1 will not be able to use backward induction to solve this problem. But since this is not 2 but it is 0, since this is not 2 and 0, player 1 knows that player 2 will play y at this node because utility of y is more than n. And you see, y is a dominant strategy for player 2. And therefore player 1 knows whatever I choose, whatever action I choose, player 2 will always choose y. Is this correct? Because at each node, at this node or this node or this node, player 2 will always choose y because utility of y is more than n, utility of y is more than n, utility of y is more than n. Therefore, whatever I choose, player 2 will always choose y. Now player 1 knows, okay, player 2 will choose y. Now the game will be reduced. We'll have a reduced game, L, C, and R. At this node, you see, this is the dominant strategy player 1, player 2 will play, and the utility will become 2, 1. At this node, this will be the outcome if player 1 plays C and player 2 plays Y. Therefore, this is the utility at this node. And this will be the outcome because Y is dominating X. Therefore, 0, 2 will be the utility at this node. Now player 1 can decide what action he should take. You see, L is giving him highest outcome. Therefore, player 1 will play L and player 2 will play Y. And this is actually the subgame perfect Nash equilibrium in this game, or the Nash equilibrium. Both are same in this game. I will give you one more example where subgame perfect Nash equilibrium and Nash equilibrium are not same. So I will actually I didn't say the correct I did not tell the correctly. It is actually where Nash equilibrium, all the Nash equilibriums are not subgame perfect. We'll see that example as well. Over here, the subgame perfect Nash equilibrium and Nash equilibrium both are 1. Therefore, both are same over here. Player 1 is playing L and player 2 is playing Y. Is this all right?
I'm
or have
okay.
Okay. If I confuse you, you can just interrupt me and I'll just go back and let you help you. All right. So this is what the Nash equilibrium is. So it will be L comma Y. This is the Nash equilibrium for this game. Okay. So this is the next game. In this, we have the same question. How many subgames are there in this game? So you see, in this game, we don't have a dotted line. Therefore, this is not a simultaneous game. We are playing a sequential game. Player 1 is playing and he has 3 strategies, C, D, and E. Then player 2 has 3 decision nodes, and at each decision node, he have different strategies. F, G at the first node, H, I at the second node, and J, K at the third node. And the utilities are also written over here. So the first question is, how many subgames are there in this game? So let us identify the subgames. You see, this is the first subgame. This is the second subgame. This is the third subgame. And this is the last subgame. So there are 4 subgames in this game. Is this all right? So how many proper subgames are there in this game? So this answer is actually 4. So you see, this is not a proper subgame. So there are 3 proper subgames in this game. So we'll have an answer as 3. Now comes a question where it is asked, write down the strategies for player 1 and player 2. So for player 1, it is simple. Player 1 is have only decision to make at one node. Therefore, he has 3 actions which will become the strategies. It will be C, D, E. Now you will have to help me write the strategies for player 2. Please help me write the strategies for player 2. First, tell me how many strategies have player 2 have? All right, make it more simple. Give me one strategy player 2 will have. Just one.
F and J.
F, sorry, F, H, J. All right. So you are correct. F, H, J is one strategy for player 2. So how many strategies player 2 will have? Player 2 has 2 strategies here, 2 strategies here, 2 strategies here. All combinations will actually be 2 to the power 3. And if you write all these strategies, you can just write it. It will be F, H, G, sorry, not G, J, F, H, J. Similarly, F, H, K, not G. You can just go to F, H, F, I, J, F, I, K, and so on for G. So this will be 4 and this will be 4. And therefore 4 plus 4, 8 strategies for player 2. Is this all right? Now the next question is, find the Subgame perfect Nash equilibrium for this game. Subgame perfect Nash equilibrium. So while you think, I'll just complete the strategies for player 2 because I'll upload these slides. Think about it. I'll just write it. Fij, Fik, GHJ, GHK, GIJ, and GIK. Alright. So how will you find out the subgame perfect Nash equilibrium for this game? So you can use backward induction over here.
So what is the payoff of G? It is 1 and 6 or 1 and
6. I'll just write it again. All right. I'll just write this again.
So then 6 is the highest.
I'll just draw the table more clearly over here. Just let me draw it. 1. So the game is actually C, D, and E, and 2 and 2. He has F and G, 3, 0, 1, 6. For this he has H and I, 1, 1, and 2, 1, and he has 2 over here, J and K, with 2, 2 and 3, 5. Now you can just use this. So you see, at this node, player 2 has 2 actions, F and G. Now tell me what action will 2 take at this node? What action 2 will take at this node? Over here the utility is 0, over here the utility is 6. So if 2 is rational, what action will 2 take? Over here, when 2 is playing G, he is getting higher utility as 6 as compared to 0. Therefore, 2 will play G. Is this all right?
Yeah.
And at this node, you see, player 2 will get 2, and at this node, player 2 will get 5. So player 2 will play K at this node. Now, an interesting thing happens at this node. You see, player 2 is indifferent of playing H and I. It can either play H or I. Now, this is another limitation of backward induction where such case happens. When such case happens, player 1 will not know. So player 1, what player 1 is doing? Player 1 is anticipating what player 2 will play. And in this case, player 1 doesn't know. So when this node comes, player 1 doesn't know what player 2 will do. Therefore, you cannot use backward induction, the idea of backward induction, to solve this problem over here. Therefore, you have to use the subgame perfect, the idea of subgames over here to solve this problem. So in this case, you see, you can either play H on I. Now you can just convert this game into a reduced game. Over here, this is 1, and when player 1 is playing C, the utility will become 1, 6. When player 1 is playing E, the utility is becoming 3, 5. Now, when player 1 is playing D, the utility will have either this or this. So player 2 can play H or I, where the utility at one end is 1, 1, and the other end is 2, 1. Now you can use the idea of normal form game to solve this problem. You see, over here, the strategies of player 1 in this reduced game is C, D, E. All right, and so I'll change the color, and the action at this node for player 2 is G, action at this node for player 2 is K. Therefore, the strategies in this reduced game will be, so we are just assuming G and K as no game because player 2 has already played. It will be H, I, or you can write it in another way as G, H, K, and GIK. Both are okay. All right. Over here it is G, over here it is I. There is no ambiguity in this node, either H comma I. So he can either play GHK in the whole game. In the whole game he can either play GHK, or in the whole game he can either he can play GIK. Now you can draw the table for this game. So the player 1 has 3 strategies. It is C, D, and E. So it can either be C, D, or E. And player 2, so this is for player 1, and for player 2 he has 2 strategies, GHK and GIK. All right, is this okay? This is the game table for this reduced game. Now you can just populate. So when player 1 is playing C and player 2 is playing GHK, the utility will be 1,6. Just check if this is correct. When player 1 is playing C and player 2 is playing GIK, the utility will again be 1,6. When player 1 is playing D and player 1 is playing GHK, then this will be reached and the utility will be 1,1. And when player 1 is playing D and player 2 is playing I, the utility will become 2,1. This will be reached. Similarly, when player 1 is playing E and player 2 is playing GHK, then the utility will be 3,5, and for this also 3,5. Is this all right? You see, we have discussed a lot of things. First, we have reduced this game. Then we have defined the strategies for player 1 and player 2. We said that either you can write like this or like this. Now, for this reduced game, we have drawn the game table, and currently we are standing over here. If this is okay, then we can just proceed a little further.
Yeah, okay.
Now you can just use the idea of Nash equilibrium. You see, when player 2 will play this, player 1 is better off playing E. When player 2 is playing this, player 1 is better off playing E. Check. When player 1 is playing C, player 2 can either play any one of the strategy. When player 1 is playing D, player 2 can play any one of the strategy. And when player 2 is playing, player 1 is playing E, player 2 can also play any of the strategy. So we have marked the best responses, and the intersection of the best responses over here will give the Nash equilibrium. For this game, reduced game, we have used the idea of backward induction, and for this reduced game, we are defining the Nash equilibrium. Therefore, overall, for this overall game, this is subgame perfect Nash equilibrium. These two strategies, or these two strategy sets, are the subgame perfect Nash equilibrium. What are the strategy set? You see, player 1 will play E. So I'll just write it somewhere. I'll just erase it. Player 1 is playing E and player 2 is playing GHK. And the second one is player 1 is playing E and player 2 is playing GIK. So these two are the subgame perfect Nash equilibrium. Is this all right?
So we are calling it SPNE because we reduced the overall game to the lower subgames, and
Yes,
hence we
using
arrived
the
at.
idea of backward induction.
We still don't know whether this is the overall Nash equilibrium. That there is some other check which we have to do.
So I have a question next. Find the Nash equilibrium for this game, and we'll see that all subgame perfect Nash equilibrium are Nash equilibrium, but not all Nash equilibriums are subgame perfect Nash equilibrium. So I'll write it.
Okay.
All subgame perfect Nash equilibrium are Nash equilibrium, but not all Nash equilibrium are subgame perfect Nash equilibrium. Okay. So we have seen what is the subgame perfect Nash equilibrium for this game. The next question is find the Nash equilibrium of this game. All right, I'll just draw this again. So I just use over here. So it is 1 C D and E. Okay, I'll just have to make, sorry, I'll make more space. 1 C D and E. 2 will play in these nodes. 2 has 2 strategies, F comma G. This is 3 comma 0, 1 comma 6. Over here also 2 strategies, H and I, 1 comma 1 and 2 comma 1. And over here J and K, this is 2 comma 2 and 3 comma 5. All right, I have written the complete game. Now tell me, we will not use the idea of backward induction. All right, so we'll just write the strategies for the each player. The strategies of player 1 is, we have written it actually, we have written it. So these are the strategies for player 1 and player 2. We have written the strategies for player 1 and player 2. Is this correct? Now we'll draw the game table for this overall game with these strategies. All right. So player 1 has, I'll just erase this, we don't need this. Player 1 has, player 1 has 3 strategies, C, D, just draw it a little bit below, C, D and E. And player 2 has 8 strategies. The strategies are F, H, J, F, H, K, F, I, J, F, I, K, G, H, J, G, H, K, G, I, J and G, I, K. Alright, so these are the strategies for player 2. Is this okay? Why I'm drawing the game table like this? We are not using the idea of backward induction. We'll just say what are the strategies of each of the players and we'll write the utility, and then we will see what is the Nash equilibrium for this overall game. Therefore, we have written the strategies of player 1 and player 2 without reducing the game using the idea of backward induction. Now we'll just fill this. Filling is not very difficult. We'll just use this idea. So when player 1 is playing C and player 2 is playing F, H, J, then the utility will become 3 comma 0. You could just help me. This will also be 3 comma 0. This will also be 3 comma 0. And this will also be 3 comma 0. Over here, player 2 is playing actually G, then it will be 1 comma 6, 1 comma 6, 1 comma 6 and 1 comma 6. Is this all right? Am I going fast?
I'm okay.
Now when player 1 is playing D and player 2 is playing FHG, so wherever H is being played, the utility will be 1 comma 1. So I'll write it quickly, 1 comma 1, 1 comma 1, 1 comma 1, and this will be 1 comma 1. And wherever I is played, the utility will be 2 comma 1. So 2 comma 1, 2 comma 1, 2 comma 1 and 2 comma 1. All right. In this game where player 1 is playing E and player 2 is playing J, wherever J will come, we'll have 2 comma 2. So I'll just write 2 comma 2, 2 comma 2, 2 comma 2 and 2 comma 2. And for K, we'll write 3 5. So this is 3 comma 5, 3 comma 5, 3 comma 5 and 3 comma 5. All right. Now we'll use the idea of best responses. So when player 2 is playing, I'll use another color. So when player 1 is playing this, we have highlighters also. No? So when player 1 is playing this, player 2 is playing this, the best response of player 1 is to play 3. Over here, player 1 can either play this or this. You see, the utility in this case is 3 for player 1 to play C or to play E. In this case, player 1 will play E because this will be the action for player 2, and the best response for player 1 is to play C. Over here he can either play C or he can play E. Over here he has to play E because the utility is 2. Over here he will play E. Over here he can either play D or E, and over here he will play E. Is this all right? The best responses of player 1. Similarly, we can do this for player 2. So when player 1 is playing C, the best response of player 2 is to play these 4 strategies, either of the 4 strategies. When player 1 is playing D, you see he is indifferent in playing any strategy. He will get 1 in all the strategies. So all will be his best responses. And when player 1 is playing E, he will play 5 is here, 5 is here, 5 is here, and 5 is here. Now we'll see where the best responses intersect. You see, best responses intersecting here, 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 and here. So there are 5 Nash equilibriums for this game. What are the Nash equilibrium? Where player 1 is playing E and player 2 is playing this, 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 and this. And the other is when player 1 is playing D and player 2 is playing this. So there are 5 Nash equilibriums for this game. Is this all right?
How does it compare with SPNE?
Right. We will do just that now. We'll do that. All right. So you see, we have SP. So SPE, we can say it is E GHK and E GIK. So E GHK and E GIK. But Nash equilibrium is giving me more. He's saying you can also play E FHK and FIK.
Sorry, it will be the last column, not the second last column.
Yes, sorry. Yes. And this is extra. This is also extra. You see, when you play D and the other player is playing GIJ, this is very different. What is happening? The player 1 is playing D and player 2 is playing GIK. So this will be the outcome. Now you can think, why will such outcome come as Nash equilibrium? Because in that
so
case,
you are saying there are. Are you saying
sorry.
there is only one Nash equilibrium out of these 5? What did you just
say?
No.
I'm not saying there are 5 Nash equilibriums for this game and 2 subgame perfect Nash equilibrium for this game. Yeah. So I'm asking the question, why we are having more number of Nash equilibrium? And so my question is, how subgame perfect Nash equilibrium gives me more information or more. So how this Nash equilibrium and subgame perfect Nash equilibrium are different from one another? So what does this difference mean? Where does this difference come from, and why? What does this difference signify? That is the question I'm asking. Is the question clear? So you see, when we have a subgame perfect Nash equilibrium, the outcome is 3, 5. But in Nash equilibrium, the outcomes are 3, 5. But there is one more outcome which is less than 3, 5, which is 2, 1. And it is less than for both the players, not only for one player, it is less for both the players. That is why I was highlighting this utility set. Because this is very peculiar. The game can end at 3, 5, right? But Nash equilibrium is saying you can also end at 0, 1. Instead, subgame perfect Nash equilibrium is not saying that this is a subgame perfect Nash equilibrium. Subgame perfect Nash equilibrium is only giving 3, 5 and not 2, 1. Is this question clear?
Question is clear, answer is not.
Answer will be given in the next. This will give one idea of how and not how. So what is this idea? Why these two equilibriums are different? All right, we'll see this with this example. Just I wanted to give that question to your mind. All right, so this question is clear, right? We have 2 subgame perfect Nash equilibrium and 5 Nash equilibrium. Is this clear?
Yeah.
So this problem is done. So we'll go to the next problem. So this is also a similar game. We have to say how many subgames are there, how many proper subgames are there. We will define the strategies of the players, then we'll find out the Nash equilibrium for the players, and then we'll find out the subgame perfect Nash equilibrium for this game, and then we'll see what um, I'll not actually define how these two are different because this will need more ideas, but I'll give you an intuition what these two equilibriums, where is the difference. All right. So how many subgames are there? You see, this is one subgame, this is another subgame, this is one subgame, and the whole game is also a subgame. So there are 4 subgames in this game. Is this clear? There are 3 proper subgames in this game because we'll exclude the whole game. Now tell me the strategies for player 1 and for player 2. Please help me with this.
P1 is A, G, A, H, B, G, B, H.
A, G, A, H, B, G, B, H. All right. So I hope this idea is now clear. For player 2,
Again 4.
C,
E,
E,
C, F, D, E, D, F.
C, F, D, E, and D. All right. Now we can. So we have done till this question. Now we can identify the Nash equilibrium for this game. We'll draw the game table quickly. This is for player 2. This is for player 1. And the strategies for player 1 is A, G, A, H, B, G, B, H. And this is C, E, C, F, D, E, and D, F. All right. Now we can write down the utilities. One thing you will identify very quickly is, you see, this game table is not a very confined representation of a game. In the previous one, you see you had 1, 2, 3, 4, 5, 6 utility, but in this game table you have 8 into 3, 24 places you have to write utility. Therefore, this game table is not a very efficient way to represent a game. All right. Over here also you will see that you have only 5 utilities written in 5 places, but over here you have 4 cross 4, 16 places you have to write the utilities, and many places the utilities will be repeated. Therefore, this is not a very efficient way to represent a game. All right. So A, G, and C, E. So A, G, and C, E. What will be the utility? Please help me.
3, 8.
3, 8. A, G, and C, F will also be 3, 8. This will be, so D will be played 8, 3 and 8, 3. A, H, and C, E. When A, H, and C, E, it will be 3, 8. A is there, so it will be 3, 8. This will be 8, 3 and 8, 3. All right. Now we have B and G and C and E. So it will be 5, 5. Again, BG and CF. So when we have B, G, and C and F, the game will come over here. Alright, so it will be 2, 10. BG and DE, the game will be 5, 5. Please confirm. If you have doubt, you can just ask me. Alright, I'm just writing it, but if you don't understand, please stop me. Again, B and G, and the strategy is D and F. So the game will come over here. It will be 2, 10. The second strategy is BH. So this is actually BH. All right. So B and H. So I just erase all the parts. These things. And we have B, H, and CE. CE. So it will be 5, 5. CF. So it will be 1, 0. Again, D, E, 5, 5. And D, F, it will be 1, 10. All right.
1, 0.
Okay. Yes. 1, 0. 1, 0. All right. Now we'll identify the Nash equilibrium for this game quite easily. You see, when player 1 is playing, so when player 2 is playing CE, when player 2 is playing CE, the utility of player 1 is maximum for these two strategies. When player 2 is playing CF, then it is maximum for these two strategies. When player 2 is playing DE, it is maximum for these two strategies. And when player 2 is playing DF, it is maximum for these two strategies. Alright. Now we'll see for player 2. So when player 1 is playing this, player 2 will play these two. When player 1 is playing this, player 1 will again play these two. When player 1 is playing this, player 2 will play this and this. And when player 1 is playing this, then player 2 will play this and right. So the Nash equilibrium for this game is this block, and this block. So there are 3 Nash equilibriums in this game. I'll write down the Nash equilibriums. So Nash equilibriums are BH, CE. The second is AG, CF. And the third is AH, CF. Is this clear? 3 Nash equilibriums for this game. Now we can quickly identify the subgame perfect Nash equilibrium using backward induction. Alright, so you see in this subgame, player 1 is playing at this node. Now player 1 has a utility of 2 when he plays G, so he will play G and not H. Alright, he will not play H. Now player 2 knows that player 1 is rational and thus his utility is more when he plays G. Therefore, he will get a utility of 10 if he play F and a utility of 5 if he play E. Therefore, he will play F at this node. Is this alright? And not E, player 2. At this node, player 2 will get 8 and at this node he will get 3. So he will not play D, he will play C. Now player 1 knows that player 2 is rational and therefore he knows that when player 1 is playing B, then player 2 will play F and player 1 then has to play G and he will get a utility of 2. On the other hand, if player 1 plays A and player 2 will play C, he will get a utility of 3. Therefore, you can see very easily that player 1 will play A and player 2 will play C, and this will be the equilibrium. But you have to identify the strategy. We have identified the action. So player 1's let's erase this. Player 1, what will be the action of player 1? Player 1 will play A and at this end he will play G. So AG. Player 2 will play C and at this end player 2 will play F. So CF. This is the subgame perfect Nash equilibrium for this game, and this is the Nash equilibrium for this game. So you have only one. You see only one equilibrium which is matching as subgame perfect and Nash equilibrium. There are 2 other equilibriums in Nash equilibrium which is not subgame perfect. So you can, is this clear? Then we can move forward. Is this idea clear? We have 3 Nash equilibriums and 1 subgame perfect Nash equilibrium.
Okay.
Right. Now you see when player 2 is playing CE, he will get a utility of 5, 5 when player 2 plays B at BH. Alright. And when player 1 is playing AG and player 2 is playing CF, then the
You marked that
utility of
incorrectly. Actually, you should have. The SPNE is AGCF.
no, I'm not marking SPNE. I'm marking NE Nash equilibrium. All right. So I'm marking this strategy set. So I'm saying player 2 is playing CE, C and E, and player 1 is playing B and H. So the utility will be this 1, 0 for this Nash equilibrium. Is this clear?
It will be 1 and 0. It will be 5, 5, right?
Okay, sorry, 5, 5. Yes, sorry. It will be 5, 5. And for this case, when he's playing A, G, and player 2 is playing C, F. So when he's playing A,
No, that is the
G,
SPNE. AGCF is the SPNE.
but it is also Nash equilibrium, right?
Yeah.
So A, G, and C, F. Then this is the utility for both the players 2, 10.
No, it is 3, 8. No? A, G, and C.
A, G, and C, F. Yes, 3, 8. I'm sorry. All right. And at this end, when he is playing A, H, and C, F. Yes. When he is playing A, H, and C, F, then this will be the utility A, H, and C, F. No, this is the utility. I'm sorry. Okay. Is this all right? Now you see, you may ask, why will this BHCE a Nash equilibrium? Because this is not a very good strategy to play. You see, when the player 2 is playing, I will play H. I will play H when you play B. When you play B, and I will play F. Just a minute. Have I written everything correctly? BH and I have written.
So when he plays B, this guy will place E. Because he has 5 greater than 0. No? He'll not play. H is player 1 ka strat.
Yeah, H is player 1 ka strategy. A, G, C, F, and B, H, C, E. Yeah, I'm correct. So I was telling you, sorry, what you were telling? H is player 1 ka strategy, right? So so actually this is actually what? This is a threat. Player 2 is saying, if you will play B and H. So you see, when he plays B and he plays H, so player 1 is actually giving a threat to player 2. Player 1 is giving a threat to player 2, saying that if you are going to play F, then I will play H, and your utility from 5 will go to 1. So Manisha, can you mute yourself if you're not speaking? Right. So I'm saying player 1 is giving a threat to player 2. He's saying, if you play F, I will play H, and your utility will come from 5 to 0. But in that case, you see, when he's saying, then if you are playing F, I will play H. He is forcing player 2 to play E instead of F. But this threat is not credible. This threat is not credible. If the utilities are changed, this threat may become credible. All right, because he has a utility. So you see, this game is actually ending at subgame perfect Nash equilibrium at this point. If this point was not there, then this threat would have been credible. All right, this threat would have been credible. This is not a credible threat. In such cases, when the subgame perfect Nash equilibrium, and there are some other points in which the utility will be less than what the subgame perfect Nash equilibrium is giving, then the players can give threat using this Nash equilibriums. So actually what is happening is player 1 is saying, if you play F, I will play H, and this will be, your utility will come down from 5 to 0.
Even though technically when player 2 plays F, player 1 between G and H, if he plays G, he will get 2
Yes,
greater than 1.
yes. So suppose in this case it was not 2, it was 0. Then this threat would have been credible. Then player 2 knows that if I play F, then player 1 will play H. So this thread is not credible, but some cases it may become credible. I don't have an example over here. I will find one example and then I'll maybe discuss this in the next class. But this is how this Nash equilibrium and subgame perfect Nash equilibrium differs. All right, so there's some idea called credible thread and non-credible thread, and over there, because this idea is not discussed in sir's lecture, but I wanted to bring it over here, and that's why I tried to incorporate in this problem. Actually, this is a made-up problem, and I'm trying to incorporate this idea. That's why it's not very clear, but this is where the difference comes: Nash equilibrium and subgame perfect Nash equilibrium.
So any Nash equilibrium which is not a SPNE tends to become a non-credible threat. That's the summary.
No, I'm not saying that. I'm saying that in this game, this Nash equilibrium is a non-credible threat. It may become credible threat also. So I don't have an example right now. I'll try to find an example and discuss this idea next week clearly. But this is where the idea comes from: credible threat and non-credible threat. I'll try to incorporate one problem next week and then we'll discuss this more. All right. Before that, to solve the problems in this assignment, you have to find out these things. What is the Nash equilibrium? What is the subgame perfect Nash equilibrium? The strategies and all those things. So whatever we have discussed, you can use those to solve the problem. This idea of what is this, it is separate from the discussions on professor's lecture. All right.
Okay.
So shall I move forward?
Yeah.
Okay. So this is an interesting game. So this is an infinite prisoner's dilemma. So we have seen a one-stage prisoner's dilemma where they can either cooperate or defect. So I have used this cooperate and defect, idea of cooperate and defect. So when both cooperate, they get a utility of 3. When one defects and one cooperate, the person who is defecting gets 5 and the other gets 0. And when both defects, they get a utility of 1. All right. So we can just draw one table for this and we can solve it for one period. But this is an infinite period game, and this idea is coming from cooperation. All right, cooperation, and this idea will be discussed in the lectures very soon. But since this is an extensive form game where one game affects the other and both are playing simultaneously, so there are multiple stages in this game. That's why I have included this game over here, where we have infinite period game. All right, but you see, when you have 100 rupees now, that 100 rupees, if you keep it for 1 year or so, that will get reduced in amount because of inflation. So there is something called discount factor. So if you have 100 rupees now, that 100 rupees will not be 100 1 year from now. It will become 92, 96, 94, whatever is the rate of inflation. And this is known as discount factor. So we'll say if X is the amount now, this will become delta times X sometimes from now. And that sometime is actually 1 year in this consideration when I say discount factor. So this idea of discount factor is clear, and why I am bringing this here is because we have multiple periods. So in this period, if I have X, in the next period, that amount will become delta times X, and where delta is less than 1. Delta is actually less than 1. So this discount factor is clear?
No, I did not follow.
Okay, I'm saying that if you have 100 rupees right now, and if you keep that 100 rupees with you in the for the next year, there will be inflation, and that 100 rupees, the buying power of that 100 rupees will
finance
reduce.
Discount power. Okay, yeah.
Yes. So that is what I'm saying. If you have X now, in the next period, it will become delta times X. All right. So this is what discount is, and why I have bring this discount is because we have multiple periods, and when we have multiple periods, some amount which you are earning then will have lesser impact than what you are earning now. All right. So the utilities are, so I just quickly draw the game table. So one is cooperate and the other is defect. Cooperate and defect. This is player 1 and this is player 2. Player, if both cooperates, they will get 3,3. If one defects, so whoever is defecting will get 5 and the other is getting 0, 5, 0, and this will be 1, 1. All right, so this is the utility. Now you see, we are saying assume players discount future payoff as delta times factor delta. What is the condition for delta? At what delta this will happen? What is this? I'm telling you. You see, this says grim trigger strategy. It means that we will cooperate until one point when someone defects, I will also defect. It means that we are cooperating for some period of time. Both are cooperating. I will also cooperate and you will also cooperate. The strategy will be cooperate, cooperate. But if you defect, I will defect forever from the next period onwards. And the other way is also true. If I defect in this period, you will defect forever from the next period. This is what grim trigger strategy is. It is just like revenge. Revenge. You have defected, wait for me, I will defect from the next period onwards forever. Is this clear? Now we have to find out that value of delta which gives a subgame perfect Nash equilibrium. Is the problem clear? This game is played for infinite horizon. What is the game? The game is prisoner's dilemma, and the future payoff is getting discounted, and we are trying to find that delta for which this game trigger strategy is triggered, and the game becomes a subgame perfect Nash equilibrium. We have to find that subgame perfect Nash equilibrium, that delta. We have to find that value of delta such that the game becomes subgame perfect Nash equilibrium. You see, what are we saying? We are playing CC. So we are playing CC for some number of periods. Once someone has played D, C or C, D, either can happen. Either C, D happens, matlab player 1 is playing D and player 2 is playing C, or the other way, player 1 is playing C and player 2 is playing D. Then from next period onward, this is for only one period. Only one period. All right. From the next period onwards, everybody will play D, D. For some number of periods, C, C is played. Then someone plays D, C or C, D, and therefore from the next period onwards, D, D is being played. All right. Now we will evaluate this for one of the players, and we will understand what will happen. And because this game is symmetric, the same will happen for the other player as well. So it doesn't matter if we are solving it for one player or the other player. Now, what is the payoff? Payoff for cooperation for C. What is the payoff? The payoff is 3. You see? So this is for one of the player, only for player 1. So player I am saying. Payoff for player I when C is being played is 3, plus in the next period it will be delta times 3. And again in the next period it will be delta 3 times delta square. All right? It will be 3 times delta square. And again in the next it will be 3 times delta cube and so on. Till some point. We have to find that point, and that point will become, we will see how that becomes subgame perfect Nash equilibrium, but we have to find that point. All right. Now payoff when D is played first. So when D is played first, the first utility for this player will be 5 because he has played D first. When he has played D first, he gets 5, and the next time it will be 1 times delta, 1 times delta square, 1 times delta cube, and so on. Because he is defecting, the next time both the players will defect. And this will be the utility for infinite horizon. So this is the utility when both are cooperating. This is the utility when he has played delta and then both are defecting. So this is what dream strategy is. Cooperate for some number of points until other defects and then defect forever. Is this
He need
idea
not
clear?
he need not defect. He can defect at stage 3 or stage 4 also.
It
But
can
we are
be any
assuming.
stage. No, we are not assuming anything. We have to find that stage, that value of delta, and that. So this value of delta will define what is that stage is. Suppose we will get that to that value of delta. Suppose the value of delta is 0, for example. So if the value of delta is 0, this sum will become 3, and this sum will become 5. Therefore, defecting is better for him. He will defect, right? Because 5 is more than 3.
Okay.
We have to find that delta. That value of delta will tell me what period at which he shouldn't defect, or he should cooperate, till which point he should cooperate. So what we are saying is, this is the utility when he is cooperating, this is the utility when he defects first. Now, if this value of cooperation is more than this value of delta, he will never defect. So 3 plus, so actually this sum will become, so I'll write it over here. So if you know infinite sum concept, this sum will become 3. So this is 1 and this is delta. So it will become 3 plus 3 into. So it will be equal. So it is equal to 3 times 1 by 1 minus delta. So this is delta is the r in geometric progression, and it will be 3 into 3 into 1 minus delta. And this sum will be 5 plus. So this is 5 separate. And over here 1 comes, so it will be 1 minus delta times 1 minus 1 plus delta times, okay, it will be delta times 1 minus delta, because it starts with delta, so it will be delta times 1 minus delta. So this is the sum. It starts with actually 1, so if you take out, I'll just write it properly. So if you take out 3, it will be 1 plus delta square plus so on, and this sum is actually 1 by 1 over delta. And over here, if you take 5 plus 1 common, it will be delta plus delta square plus and so on. So this sum is actually delta by 1 minus delta. Alright. Now what I am saying is, if this value is more than this, then there is no point in defecting. So 3 times 1 minus 1 by 1 minus delta is equals to 5 plus greater than equal to 5 plus delta by 1 minus delta. Then the game will continue and there is no defect. So it will not defect. It will always continue to cooperate. So this condition of delta, for which cooperate until other defects. So I will not defect. Why will I defect? Because defecting will give me lower payoff. In this case, when this is more than this, then I will not defect. What is the point in defecting? My payoff when I cooperate is more than if I defect first. Why will I defect? Is this idea clear? If my payoff for cooperation, this is the payoff for cooperation, is more than the payoff for defecting, I will never defect first. Is this idea clear? Then we'll see what is the value of delta. You can unmute yourself, or I will just do the question again if it is not clear.
But you have written I'm defecting first.
Right. So this expression, this inequality, what it is saying. Suppose, so over here the utility, this utility is when I defect. This utility is when I cooperate. All right. So this is when I cooperate. This is when I defect. What I'm saying is, when I cooperate, if that utility is more than what I will get when I defect, then why should I defect? I will not defect at all. I will let the other person defect. I will not defect first. I have some utility when I'm cooperating. This is the utility when I'm cooperating.
No, I've understood that. What you're saying is if that other guy defects, then anyway my utility will drop from 3 to 0, right? So anyway I'm losing out. If
1. So at one point it will be 0, otherwise it will be 1 forever, right? So you see,
yeah,
when both defects, there is no game to be played. You see, where both are defecting, both will get 1 for infinite amount of time with discount. So there is
correct.
no, this strategy when defect forever will not change, right? It will always go on. So 1
Correct.
plus delta times delta squared, it will always go on. The thing which can maximize his utility is this 3, because there is some strategy which can change 3 to 1. 0 is there in between, you can neglect that point. It can change its strategy value from 3 to 1, which is worse, right? Why will I get 1 if I can get 3? So both players, what will they think? I have a utility of this value when I cooperate. But if I defect first, my utility will become this. This is actually sum for infinity, right? So my utility will become this. If this utility, if this utility when I cooperate, if this is more than what will I get if I defect, then why should I defect? I will not defect. I'm getting more if I am cooperating. So this is the expression which says, if this is true, I will cooperate. If this is not true, I will not cooperate. I will defect in the first iteration only. Why should I wait?
Okay.
So if you solve this, you will get a value of delta. I'm not solving this because it will be time taking, but this is just a linear expression in delta. Not linear, it is quadratic. Never mind, you will get a value of delta which is greater than some value. All right. And if delta value is greater than that value, whatever that value is when you solve it, then the player will never defect. They will cooperate forever. There is no incentive for that player to deviate to defect. They will always cooperate. And this is how cooperate game theory, the idea comes, that we are cooperating until you defect. If you defect, I will also defect.
Okay.
So this is an example of ultimatum game. So in an ultimatum game, player 1 is playing first. All right. And he has infinite strategies. In this game, I have limited it to some number of strategy, but suppose he has infinite strategies from 0 to a value. Over here I am saying 10, right? Now if you say infinite, then we are saying that he has a value of 10 or $10, and he can divide this is any amount, 0.0001, 0.0002, but in reality it is not true. You can have only 1 cent or 2 cent, you cannot go beyond this. So I am in discrete game only. So what I'm saying is he can either play 0, 1 cent, 2 cent, 3 cent, and he can go till 10. Right? You can take this game infinite also. So infinite strategies also. If you say you can divide this at any value. All right. Now player 1 has $10 and he can split this value and give some amount to player 2. Player 2 can either accept or reject. If player 2 accepts, the money is split accordingly, and if player 2 rejects, both gets 0. Determine the subgame perfect Nash equilibrium. So this is the same problem which was discussed in the class. But why I have taken it over here is because in the class example, sir has taken one example where we have discrete values. Suppose 0, 1, 2, 3, and so on, discrete values. In that case, it was discussed. In another case where you have value from 0 to 10, any number can be there. That case was not discussed very clearly. So we can take this case also and this case also. For both the cases, we will see what is the Nash equilibrium. All right. So for the first case, we are saying that we have discrete values. So for discrete values, player 1 can either, so for simplicity, we will just assume it is 0, 1, 2, 3 till 10. So player 1 can either give 1 to 10, any value positive amount, so that is positive amount, or he can give 0, any positive value or 0. So when he gives positive value, player 2, so suppose I'll just draw the game. So it is player 1 is playing and he can give X. Now player 2 has two strategies. Either he can accept or reject. So when he accepts, the utility of player 1 will become 10 minus X and utility of player 2 will become X. And when he rejects, it is 0, 0. Is this game clear? And for now, we are assuming this X to be discrete, 0, 1, 2, 3 and till 10. All right. Now, if he plays a positive value, so you see, this will be positive, not 0. And in such cases, player 2 will always accept or not reject. because if he rejects, the utility is 0. Therefore, whatever value player 1 gives above 0, not 0, above 0, then player 2 will accept. And that is a subgame perfect Nash equilibrium. Now, when player 1 is playing 0, he can either, because you see this will become 0, and player 2 can either accept or reject. Either accept or reject, and in that case, you are not sure. So player 1 is not sure what player 2 will do. Is this all right? When player 1 is playing, so you can write when player 1 is playing positive strategy, player 2 will play accept. When player 2 plays 0, when player 1 is playing 0, player 1 plays 0, player 1 plays 0, then player 2 can either play accept or reject. In that case, you can have both as the Nash equilibrium. Accept, 0 accept and 0 reject, both as Nash equilibrium. Now, the interesting thing happens when this is not discrete, when this is continuous. You see, any value x greater than 0, when any value of x greater than 0 is given, in that case, player 2 will accept. But you see, any value greater than 0 is not defined. You cannot define a value which is just greater than 0. If you do that, you actually cannot do that. You cannot define a value just greater than 0. Is this clear? Therefore, you will not have a subgame perfect Nash equilibrium in this case. You know the strategy of player 2. Whenever player 1 plays a positive strategy just greater than 0, player 2 can play accept, will play accept. But this strategy, x greater than equals to 0, is actually not defined. Is this clear? Am I making sense or not? Anyone here?
When it is discrete, you are saying it makes sense because x
Yes.
is equal to 1, but when
You
it is
can-
continuous, it can be 0.0001, and that is why you are saying
You
it is
can-
not.
Yes, you are not able to define the best response of player 1. You are not able to quantify the best response of player 1. Best response of player 1 is undefined. That is why that equilibrium is not defined. So best response of player 1 when player 2 plays accept is not defined. You cannot give a value to that point, and therefore that will not be a Nash equilibrium, a subgame perfect Nash equilibrium or Nash equilibrium in this game. That is not defined at all.
But the questions comes is if player A, player 1 is giving one offer and player 2 is rejecting that offer. Because out of 10, he can split in any ways, like 1 to 5.
So you see, the idea of Nash equilibrium is what? The players try to maximize its payoff. So when player 2 is playing A, what will player 1 do at Nash equilibrium? Maximize its payoff. When will the payoff be maximized? When he gives very, very less value or just 0 value. And this just 0 value is not defined. I know he can give any value, but we are talking about Nash equilibrium. Nash equilibrium is what? At that point at which he maximizes his utility. It is very specific. And he'll not be able to maximize his utility because 10 minus x, you will not be able to say just less than 10 because it is not defined. That value is not defined mathematically.
But in that case, if player 2 completely reject the offer, none of them get anything. Then how does it goes?
No, you see, I just write this. So player 2 can have two strategies. So we are talking about player 2, all right? Player 2 can have two strategies. First strategy is, I just write it clearly, otherwise I can make doubts. So if player 1 says player 2 is saying the first strategy is accept all, whatever is there, accept all. Accept all. The second strategy, player 2 can say accept if x is greater than 0 and reject if x is equals to 0. Alright, this is the two strategies player 2 can play. So when player 2 is saying accept all, player 1 can give any values. So you see, we are actually saying accept all. Whatever player 1 gives, you should accept. So player 1 giving any value, either 0 or either greater than 0, any value he can accept. But you see, this will not become when it is 0. And so when x is 0, so what is the utility of player 1? It is 10 minus x, and utility of player 2 will be 0 when x is 0. All right, so it is 10 and 0. So this in that case, I'll just draw the game to make it clear. This is player 1 and this is player 2. He has accept and reject. In this case, the utility is 10 minus x comma x, and in that case, it is 0 comma 0. So when the strategy of player 2 is accept all, whatever it is there, and player 2 is giving a positive value, so it is something. Suppose it is 1, so we will have 9 comma 1, and it is 0 comma 0. So this strategy accept all is not correct, is not a Nash equilibrium, because when he is giving 1, it is more than 0. But when he is giving 0, it can either be 10 comma 0 or 0 comma 0. So in that case, the utility in any way except all, this any strategy of player 2 will have the utility of player 2 maximized. So in this case, the utility of player 2 is maximized. Whatever player 1 gives, 0 or greater than 0, the utility of player 2 is maximized. 0 if it is x is 0, 1 if it is x is 1, 10 if x is 10. So this is one Nash equilibrium of this game. But over here, this gives some complications. All right, you can just unmute yourself.
So this is not accept all. This is accepting the offer which is given by player 1. Whatever
Yes.
offer it is there. Above
So
0.
that is what.
Right? This is not accept all. मतलब अगर उसमें 0.1 दिया, 0.2 दिया, 0.5 दिया, 1 दिया, that he has to accept. Player 2 has to accept that one.
No, player 2 is saying whatever value he gives, I will accept it, either 0 or positive. You see, when player 1 is giving 0, then he is indifferent in playing 0 or in playing accept or reject, right?
Right. I got it. But आप बड़ा थोड़ा make it very simple. Not going in this way. Let's say there are 10 rupees. So player 1 has offered to player 2 that we will speak like this way. Let's say it has to be bigger than 0. Right? He has to give something like less than 1 rupees, 50 fees below that one, but he has to give something, right? And that player 2 has to accept that one offer.
So the game is not defined as giving something to player 2. Game is defined splitting that amount 10. So you can split it as 0, 10 or 10, 0.
Let's say assuming that he's giving 0, then player 2 has no offer at all. I mean 0, there is no offer. Splitting of 10 means something has to be given, na?
No, so when you are saying 0, there is some offer. Na, player 1 is giving an offer कि भाई तुमको मैं 0 दूंगा. This is the offer. Either you accept or reject. I know it doesn't matter for player 2 if he accepts or rejects, but an offer is being made, and then the player 2 has an action to take. Either he can accept 0 or reject 0. It doesn't matter if he accepts 0 or rejects 0. In both cases, the utility will be 0.
But in second case, let's say you are player 1, I'm player 2. आपके पास 10 रुपए हैं, you are not offering me anything. You are telling me you have 10 rupees, and as a good friend, you don't want to share with me. This is your offer. This is 0, correct? Practically. It is if I accept this offer, no way, you have to give me something. So you also lose 10 rupees because you are not ready to give me and I have rejected the offer. Then both lose the money. This is one condition is there. If two reject, then one also lose the money. This is one side. The
Right.
second side, when you are not offering me at all, like you are offering me 0, this is just pure offer you have given to me which has no value for me. आपके पास 10 है, आपने 10 के 10 रख लिया, आप मेरे को शेयरिंग नहीं कर रहे ना, you are not offering me anything.
राइट तो अभी तक हमने जो बोला है ये प्लेयर 2 का एक्शन बोला है. वी हैव नॉट डिफाइंड व्हाट इज द प्लेयर 1 एक्शन. तो व्हेन player 2 is saying accept all, player 1 can either give 0 or give a positive value, right? When player 2 strategy is accept all, जो भी करना है accept कर लो. So player 1 what will he do? He will try to maximize his utility, right? He can either give 0 or he can either give a positive value. But now you think अगर उसको अच्छा, you are saying when he is rejecting. So in this strategy, he is not saying, player 2 is not saying I will reject. So I am segregating the strategies of player 2. One strategy is accept anything what player 2 is giving. The second strategy is accept only if the value is positive and reject when it is 0. So we have not talked about this yet. अभी तक इसके बारे में बात नहीं किया है. This is what you are concerned about, right? When player 1 is giving 0, I will reject. Both को 0 मिल जाएगा.
Yeah, but player 1 when giving 0 itself is there is no offer. I am not able to understand how that is itself is an offer at all. आपके पास 10 रुपया है, आप मुझे दे कुछ भी नहीं रहे हैं.
So you see, this is a game. This is the way the game is defined. Player 1 is having some amount and he is splitting that amount in x and 3, x. Now, when he is saying I will give you some amount, it can either be 0 or positive. Player 2 का ऊपर है कि यार तुम 0 क्यों दिया. This is not logical. This is not fair and unfair game. The design of this game is such that player 2 can make any offer he wants, and player 2's decision is either to accept or reject, nothing else. Player 2 can either accept or reject.
So the utility will be utilized when he accepts the offer, not on the rejection.
Utility will be utilized का मतलब?
But if player 2 accept even 0 also, that player 1 has the maximum value, right?
हाँ, when player 2 accept कर लेगा तो player 1 को 10 मिल जाएगा.
That is his maximum amount, right?
Yes, maximum amount.
Yeah, this is what you are saying there, right?
Yes, okay, yes. This is the first strategy of player 1. The second strategy can be accept only if the value is positive, but reject when the value is 0. In that case, utility तो दोनों का 0 हो जाएगा. In this case, the utility will be 10 minus x and x. ठीक है? Is this correct? When player 2 has this strategy. Now, this is the thinking of player 1 now. Player 1 thinks if I give 0, then my utility will become 0. अगर हम 0 offer करेंगे, if I offer 0, my utility will become 0. Then I have to offer some positive amount. Some positive amount देना है, then only I will get some positive utility instead of 0. What should be that positive amount such that it is maximum? I have to maximize that utility of mine. So 10 minus x, what is the maximum value this can take when x is greater than 0? It can take, that value is not defined. You have to maximize this value such that x is positive. It is not, so it is x greater than 0. And x का value आपका 0 से 1 का बीच में कुछ भी हो सकता है, but not 0. So it is saying x greater than 0 and it can be 1. So what is this value which is just 0? There is nothing. इसीलिए हम लोग क्लोज्ड इंटरवल ओपन इंटरवल पढ़ते हैं. x belongs to open interval 0 and closed interval 1. x is just 0 but not 0. Now player 1, what will player 1 think? Player 1 will think I have to maximize my utility. I will not play 0 because in that case my utility will be 0. So 0 तो option में ही नहीं है. I will not play 0. I have to play some strategy which is just positive. And that just positive is not defined.
Yeah, but even if we give the higher, let's say you give me a higher offer also, not 0, because 0 above 0, okay. 0.1 is in your favor, right? That is the maximum one. 0.1 is in your favor. That is your maximum value you are getting, because then you are giving me higher than 0. You are giving me higher than 0, but this is the maximum which you want to share, because you get the maximum benefit out of that one.
Right.
How about, and then if I reject it, both lose there.
So you see, we have some assumptions in this game. We are saying that both players are rational. Second thing we are saying is we will identify the best response function of both the players, and both the players are trying to maximize their best response. Okay? Now, when So the thing, when somebody is giving me some value and I will reject, that will not happen because the utility will be 0 and player 2 will not give a utility of 0 when the utility can become positive. Suppose player 1 is offering 0.1. Let us assume this case. When player 1 is offering 0.1, player 2 will not reject because accept will give 0.1 utility which is greater than 0. Okay? This is clear. Now player 1 will think I am giving 0.1 but I can maximize this utility. This is not my best response. Best response is a value which is just positive. This is not, I can deviate. There is an incentive to deviate. अभी मेरा utility है 9.9 but I can increase this utility to more. So I have an incentive to deviate from this strategy x is equals to 0.1 to a strategy, suppose x is equals to 0.01, which will give me a higher utility of 9.99. Again, if you apply this idea, you can go to 0.001 and that will give me a higher utility. Till what point you can go? It is not defined. That point is not defined when your utility is maximum and therefore
that is understandable. That is understandable. Sorry, but आपने बोला rational.
Rational,
so when
yes.
both there are rational, let's say you are there, the offer is not rational, and they are rational. So that means the first thing is that at least I should get the equal money which you are having.
So एक मिनट, हाँ, offer is not rational, correct नहीं है, offer is unfair.
हाँ, there are rational. You said both are rational. Both are rational means both are looking for something to win. Rational मतलब
नहीं, in game theory rationality का very specific definition है. It means both players will try to maximize their own utility and has knowledge, common knowledge. So he knows कि other वाला player भी rational है and then he can identify what will be the action of the other player. That is the idea of rationality in game theory.
But let's say if we both are playing, we both are rational. Offer is not rational, we are rational. We both know that we can lose the money. But the first thing is both can go 0-0. That means ये condition नहीं होना चाहिए. 0-0 नहीं होना चाहिए. Then none of us is rational. Then both of us are irrational. That there is a money and we left that money on the table.
No, you see, this idea of this is the limitation of game theory. यहाँ fair unfair नहीं देखा जाता. Nobody sees what is fair and unfair. This structure of games we are identifying, these are having assumptions कि players are rational, players have common knowledge, they have common knowledge. These assumptions make this counterintuitive कि ऐसा कैसे हो सकता है? How can this happen? So if you read further, there is something called क्या बोलते हैं? I don't remember, but in that case, you experimental game theory, I guess. In that case, you take consideration fairness and unfairness. कि this is not fair, and in that case, player 2 will reject. कुछ भी positive, अगर 5 नहीं दोगे, 5 से कम दोगे, I will reject. Those things are not studied in this kind of games where we have assumptions of rationality and such that if you relax those assumptions, then whatever you are thinking will come into account. So this is a limitation of this subject. मतलब जो भी हम अभी पढ़ रहे हैं इसका limitation है.
So I give you an example. You have to tell which one is rational, which one is not rational. Practical, क्योंकि this is more difficult. मंदिर के बाहर मैं पूरी बांटने गया था. जो बाहर भिखारी बैठे रहते हैं ना, तो वो जैसे रहता स्टार्टिंग में दो दिया, लास्ट में एक बच गया था. जो लास्ट वाले भिखारी को जब दिया तो उसने कहा एक नहीं भैया दो. He is looking at the other one there.
You are mute now.
Sorry, did you hear what I was telling?
हाँ, लास्ट में एक बच गया.
एक बच गया तो लास्ट वाले को वही दूंगा जो बचा था. उसने कहा भैया एक नहीं दो.
Right.
ठीक. So he is getting free. Let's say in a game theory he is getting free because I am the one who is giving, and according to me I am giving the best one. But so यहाँ पे मतलब उसने बोला एक नहीं दो, जबकि he is getting free on that part. So how does this game theory fits here?
So over there, rationality is not getting played. Fairness is coming. Now you are saying that I am getting 1, other is getting 2. Those things are not considered in these games. Over here, he is saying, I will try to maximize my utility. What is he offering? If that for that response, if I can optimize or give the best response from my end, मतलब सामने वाला player का response का, if I give my best response, that is the best I can do. एंड आपका जितना भी एक्शन हो सकता है सब का मैं बेस्ट रिस्पॉन्स निकालूंगा, एंड वट एवर यू डू आई विल डू द बेस्ट रिस्पॉन्स, अगर सीक्वेंशियल गेम है तो। एंड इफ इट इज साइमल्टेनियस गेम देन आपका बेस्ट रिस्पॉन्स एंड मेरा बेस्ट रिस्पॉन्स जहां इंटरसेक्ट करेगा दैट इज एन इक्विलिब्रियम। वी आर नॉट टॉकिंग अबाउट दैट, वी आर टॉकिंग अबाउट वट एवर एक्शंस यू हैव, 2-2, 3-2, 4-2, 5-2, 1-2, जो भी आप एक्शन है सबका मैं बेस्ट रिस्पॉन्स निकालूंगा। अगर आप 2 देंगे तो व्हाट इज माय बेस्ट रिस्पॉन्स, 1 देंगे तो व्हाट इज माय बेस्ट रिस्पॉन्स, फॉर एवरीथिंग यू सी आई विल एक्सेप्ट। मेरे पास तो और कुछ है ही नहीं, ऐसे भी तो 0 मिलेगा। इफ यू गिव 5 आई विल एक्सेप्ट, इफ यू गिव 1 आई विल एक्सेप्ट, so my best response in any case is to accept. That is how these assumptions are made in this theory. If you relax those assumptions, आपका जो भी consideration है that you can come, ये सब में research चल रहा है अभी, these are all in under research. एक behavioral game theory बोलता है जहाँ पे behavior study करते हैं humans का, and इसमें experimentation करके ज़्यादातर study होता है। हमारे डिपार्टमेंट में बहुत रिसर्च हो रहा है इस केस में।
How does it really plays in the market? जैसे मैं एग्जांपल देता हूँ. So we are supplying one product in Saudi Arabian market. This product was coming from a different unit. We were on and off and like this. But product is better, price were higher. There was somebody else who make the product, not the same, different product, because we are in and out. So he grabbed the market share. Then definitely we go back with a better, let's say, he reduced the price. Now the dilemma is because we are always being premium, but now we are more regular. Should we reduce the price? Should we fight with him? Should we not?
So when that entrant game was defined over here, there were many assumptions. Utility, we are not defining where these values are coming from. In prisoner's dilemma also, when we get utility, we are just saying this action is better than the other. Confess is better. So relative utility we are defining. We are not giving a value. This is the specific value of utility. We are just जब भी best response भी when we are defining, we are saying this is better than this. So बहुत सारा चीज इसमें assumptions लिया हुआ है. This utility is coming from some other theory. वहां से utility का हम लोग ideas लेके we are plugging in those values and then we are, so it is building upon some other theories. तो आपने जहाँ कहा fairness आ गया, premium products आ गया. If you consider those assumptions, then you can make one mathematical model and solve it.
But then when you were teaching before, C and D pair, let's say, both can have equilibrium, then both, then let's say if D act first, then definitely C act like D, right? Then it was D and D. If C act first, then it was C and C. But ultimately everybody make the move. I mean, one side make the move because other side has make the move already in that part. How do we interpret? If one side make the move, let's say there are two players, so one player make the move, the other has to make the move. Generally, let's say if D is making the move, then C is forced to make the move in that part.
Yes.
Right? So then the equilibrium coming is basically when C and D, C behaves like D.
So it is not forced. वही action set ही है उसके पास. These are the only action set. इसके अलावा you cannot do anything.
अब थोड़ा business.
So I think this will be similar to that market entry game. There is an entrant who is entering, and the incumbent is either fighting or accommodating. And the utilities that were defined over there, sir, it will be in that fashion, whether you are gaining market share or losing market share, or you define it on the basis of how much profit or loss you are making. And then that game theory, if you define it in that manner, which was covered in the last class, fight versus accommodate, then if we solve that, I think we'll get to an answer whether the incumbent, which is let's say you as a player who is already existing, whether he will fight or he will accommodate the new entrant. But for that, the values of the utility have to be very clearly defined, like how much you will lose if you fight, how much you will gain or lose if you accommodate. So, and the key thing is how to find those values. But once the values are known, then we can find out, because both players are rational. We know how much he is going to lose, how much we are going to lose. Shubham sir, you can say if that is the right approach.
Rationality, so the way we are solving these games, ये assumptions यहाँ पे है, real life में hold नहीं करता, and that is where research is coming. So ये जो theoretical assumptions है कि both players are rational, both have the knowledge. So until now we are saying both have perfect information, complete information. कि जैसे किसी पास कोई गेम में asymmetric information होता है. For example, government and the other firms in the country. So government has more information. When he is playing some action, the the government firms have more information than the non-government private firms. So in that case, asymmetric information comes, and there is a part of game theory which deals with asymmetric information. So over here, we are saying that symmetric information is there. Everybody knows what is happening in the game. So such kind of assumptions are there over here in this game.
This is easy, sir. This is easy where you have the information. But in practical scenario, the problem is the whole information are not there. I mean, you cannot have the whole, in real life, you cannot have the whole part of the information.
Correct.
Then how we should move, that is more important.
सर सो देखिए मैं आपको बहुत ट्रिवियल आंसर दूंगा, इससे बेस्ट आंसर मेरे पास अभी है नहीं. सो व्हेनेवर यू लर्न अ सब्जेक्ट यू गो टू द बेसिक्स ऑफ दैट सब्जेक्ट, ABCD सीखना पड़ता है, देन यू कैन अप्लाई मोर कॉम्प्लेक्स सिचुएशंस ऑफ दैट गेम. सो अभी आप ABCD ऑफ गेम थ्योरी सीख रहे हैं. If you try to incorporate more relax the assumptions and more consideration, then आपको उस समय देखना पड़ेगा कि and these ideas will help. कभी कभी क्या होता है कि this assumptions of rationality आप incorporate करें and you relax some other assumptions like common knowledge नहीं है. These assumptions will build up to that. So this is actually very preliminary subject where you are just getting the idea of how game theory works.
ठीक है sir. Thank you sir. Continue please.
And sir, you can call me Shubham. No need to call me sir. All right. So this is an interesting game, Centipede game. So ये क्या है, यहाँ पे you can get it to any stages. We have 6 stages and there are 2 players which move alternatively. So player 1 move करेगा, then player 2 will move, and then again player 1 will move, and so on. So this is 6 stages. So I'll just draw the stages. All right. So these are the 6 stages. What are the actions? They can either stop or continue. So अगर stop करेंगे, so I'll say this is stop or continue, 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 and continue. Stop, 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 and stop. Now, अच्छा, if you have seen the war of attrition, वहाँ पे क्या होता है, when players continue in the game, then utility कम होता जाता है. मतलब वो they are fighting and then the utility is actually the health. So that health decreases over time. One example of that war of attrition. Over here, it is happening just the other way around. The more time you stay in the game, the higher is your utility. All right. So one player, on one move, a player is better off playing stopping the game than continuing if the other player stops immediately. So what is happening is, if player 2 is stopping over here, then player 1 is better off stopping earlier. So when I will write the utility, it will be more clear. The game is defined like this. It is saying that whenever the other player is stopping in this stage, player 2 in this case will be better off stopping previously. All right. But worse off if the other player continues. Suppose in this stage player 1 continues, then if he stops, then the utility will be less if he continues. So I'll write the utility for one example, then it will be more clear. You can just take 1 minute and read the question again. All right, I hope you have read the question. So the question says the last player to move prefers to stop the game than to continue. So क्या है देखिए, in this utility, this is the last player and player 2 is the last player. You see the utility of player 2 when he continues is 6 instead of 7 if he stops. Now this is the same thing. The last player to move prefers stop instead of continue. You see, he will prefer stop than to continue. So this is the last statement. We'll go to the previous statement. It says that the player is better off stopping the game than continuing if the other player is stopping the game. So you see, when this player 2 is stopping, the utility of player 1 is 1. Instead, if he stops in the first stage, he will get a utility of 2. Similarly, suppose for player 1 over here, if he stops, he get a utility of 1. But if the other player in the next stage stops, he get a utility of 3. So this is what the first line means. The second line is stopping will be worse if the game continues. You see, at any point of time, at any point over here, if the player 1 stops and the game continues, so this is 2, and you see if this player continues, then his utility will be more, 4, 3, 6, 5, 8. So if this stop doesn't occur, then he's worse off playing stop. So this is what the game is. अगर second next stage में stop नहीं होता है, then his stop is worse. अगर second stage में next stage में stop हो जाता है, then he is better off playing stop. This is the game. If in the next stage someone is stopping, then he is better off stopping. If in the next stage the player is continuing, then he is better off continuing. This is how the game is defined, and this is known as centipede game because एक chain बन जाता है, and that is why it is known as centipede game. Is this all right? Is this all right?
GG.
Now we have 6 stages. So this is stage 1, 2, 3, 4, 5, 6, and this is the end. All right. The question is find the subgame perfect Nash equilibrium of this game. Subgame perfect Nash equilibrium or subgame perfect equilibrium, doesn't matter. Now we can move with backward induction. You see, I'll change the color. When player 2 is over here, what player 2 will think? Over here he is getting a utility of 6 when he continues, but gets a utility of 7 when he stops. So at this point he will stop. When player 1 is over here, he is rational and he knows that player 2 is also rational. So he will know that player 2 will stop instead of continuing. Therefore, his utility over here is 6, but he knows player 2 will stop and his utility will become 5. Therefore, in this stage, player will actually stop. Player 1 will actually stop. The same rationale goes over here. Player 2 knows that player 1 is rational and then he will stop. If he stops, the utility of player 2 will be 4. Instead, if player 2 stops at this stage, his utility will be 5. Therefore, he is better off stopping than continuing. And this will continue. Player 1 will think if he goes on, player 2 will play stop. He is better off stopping because he will get 4. So this will be the best strategy for him at this stage. Again, this will be the best strategy for this game, and this will be the best strategy for this game. Therefore, the game has this as the subgame perfect Nash equilibrium, and the strategy for player 1 is SS, SSS, and strategy for player 2 is SSS. So these are the strategies for player 1 and player 2, and this is the subgame perfect Nash equilibrium for this game. You see, this is counterintuitive. If both the players cooperate, they can get a higher utility. Both can get a higher utility. But over here, both are getting worse off. Is this all right?
So the game stops at 6 stages directly.
No, first stage. This is the first stage. This is stage 1, stage 2, stage 3, stage 4, 5, and 6. So we are doing backward induction. At 6th stage, what is the action of player 2? He will stop. Player 1 knows that at 6th stage, player 2 will stop, and therefore he will stop at 6th stage. And therefore we solved it backward, and then we saw that the game ended in first stage itself. This is like prisoner's dilemma. Both are just getting worse outcome. Not outcome, utility. All right. So this is a trust game. You see, player 1 is given $10 and he has to decide how much he will send to player 2. Now, any amount sent to player 2 will be tripled by the experimenter. So suppose player 1 is giving 5, then player 2 will actually get 15. Experimental will triple it. Player 2 then decides how much to return to player 1. When player 2 receives that amount, he has to return that amount to player 2. So the game is like this. Player 1 is over here. He is giving X to player 2. X to player 2. Player 2 has two actions. Either he can not return, so he will keep or return. So when he keeps, player 1 gets a utility of 10 minus X and player 2 gets a utility of 3X. Okay. Player 1 is given 10, he is giving X to player 2. Player 2 keeps the amount, so player 1 gets 10 minus X and player 2 gets 3X. When he returns, So suppose he is returning y, then player 1 will get 10 minus x plus y, and the utility of player 2 will become 3x minus y. Is this okay? Is this all right?
Yeah, but how much information does player 2 have?
Over here we are assuming complete information, right? Everybody knows what the other player best utility is, best responses are, utility values are, everything everybody knows. That is our assumption. Again, we have drawn the game tree. So is this all right, or any doubt is there? Player 1 is giving some amount from 10 rupees or $10 over here to player 2. Player 2's utility, if he keeps, is 3x. If he returns some amount, it will be 3x minus y, where y is the strategy. So I'll remove r by saying y is the strategy. And this is y, and I will say this is 0. The strategy over here is 0. So when the strategy of player 2 is 0, then the utility will be 10 minus x and 3x. On the other hand, if he returns y to player 1, then the strategy, then the utility will be 10 minus x plus y and 3x minus y. Is this okay? Now we will solve this game using backward induction. Okay? Is this all right? Okay. So using backward induction, what will player 2 do? You see, he is getting 3x if he gives 0, but he is getting 3x minus y if he gives y. Then what will player 2 do? What will player 2 do? This is always greater than this. 3x is always greater than 3y minus 3x minus y if y is positive. We have assumed y is positive. Therefore, player 2 will always play this strategy 0. Now player 1 knows that if he gives 0, then the utility of him will be 10 and the utility of the other player will be 0. This is the other strategy of player 1. Now, if player 1 knows that player 2, what will player 2 do? Player 2 will actually play 0. So what is good? Either to get 10 or 10 minus x. So 10 is always greater than 10 minus x when x is greater than 0. Therefore, he will not give anything to player 2. His strategy will be x is equals to 0 and y is equals to 0 for player 2. So this is the strategy for player 1 and player 2. Any questions? And this is the subgame perfect Nash equilibrium.
Yeah, continue please.
So over here also you see player 2 could have gotten more utility than 0. Over here he is getting 0. But if they were not rational and not self-interested, then they could have got higher utility, right? So this self-interested is just they are trying to maximize their utility. That is where I am written self-interested. All right. So in this game, this is the Nash equilibrium, which is worse off than other outcomes of the game. But since both are self-interested or both are trying to maximize their payoff, all are getting the Nash equilibrium actually worse off. So this I wanted to cover. This was actually discussed in not discussed in professor's lecture, mentioned in professor's lecture, but I don't have time, I see. I guess Aarti will cover this concept in the next discussion hour, so I will skip. Otherwise, if there is some doubt remaining, I will take this up in the next week also. All right, so this is the last question I had actually. It was not a question, a discussion concept. So I'll just skip this for today. I hope it is okay.
Thank you. Okay.
Yeah, that is okay. Thank you.
Thank you.